we have a good handle so far on the hyperbola. Namely, we have an equation, and we know something about it that the asymptotes exist, that they play a role in the shape of the hyperbola, and that the asymptotes are determined by the numbers in the equation itself. But there are a few things that we still don't know. It stands to reason that since all the other conics sections are dictated by a focus point or foci, that the hyperbola also would have foci. But we don't yet know, one, where they are, or how to find where they are, and two, how they help define the shape of this curve. So far it's been different for everything, with the exception of the ellipse and the circle essentially being the same. Well, actually that is kind of the same for the parabola anyways, but it's infinity, so it's not helpful. We had to introduce the directrix in order to understand how the parabola was determined. So, since the hyperbola and the ellipse share a lot of kinship, we're going to look at what we know about the ellipse and see if we can predict what the counterpart is going to be for the hyperbola. So I have written up here the two versions of the ellipse. Notice that there's going to be two versions of a hyperbola also, the horizontal, which we've been dealing with so far, and a vertical. So with the ellipse, x squared over a squared plus y squared over b squared is equal to 1. For the ellipse, and the ellipse only, I'm treating b squared as a bigger number, right? So if b is bigger than a, then this ellipse is going to be vertical, right? The major axis is going to be on the y-axis. Since b squared is under y, it's going to be on the y-axis, right? Likewise for the horizontal, if the b is bigger and it's under the x, if the bigger number is under the x squared, then it's going to be horizontal because it's going to be on the x-axis. And we discovered that the focal distance, which I'm calling c, the distance from the center to the focus point, is c. C squared is equal to b squared minus a squared. So whatever that bigger number is minus the smaller number is going to get us the focal distance squared, right? So that's how we were able to find it. And then lastly, the characteristic of the ellipse is that any point on the ellipse, if you were to draw straight lines from that point to the two foci, the sum of those two distances is going to be constant. It is going to be the same every time. And in fact, that distance is the major axis, or 2b. No jokes. Which, if we were just to, this whole thing is the major axis, or 2b. Okay? So, what do we not yet know about the hyperbola? Well, I'm going to save you a little bit of time and just kind of give you the two general equations for the vertical and the horizontal hyperbola. So we've already dealt with the horizontal, so I'm going to start with this one. So the x squared term comes first, and then minus the y squared term. So for the hyperbola, b is not necessarily bigger than a. In fact, for the hyperbola, it doesn't matter which one is bigger or smaller. What matters is what comes first, because now we're dealing with subtraction. And when we're dealing with subtraction, order counts. Not so for addition, because the associative property, commutative property, whatever the heck that is. So for horizontal, if the x squared comes first, our hyperbola will be on the x-axis, much like the one that we've been dealing with. If the y term comes first, then our hyperbola is going to be vertical. It's going to be on the y-axis. All right, so I'm just going to save you some time and just kind of give you those two general equations. So again, b is not necessarily bigger than a, but I did keep this ordering consistent, that the a squared term is under the x squared term, and the b squared term is under y squared. A squared term is under the first term, and b squared is under the second term, so that we can generalize our equation for the asymptotes. The asymptotes are just going to be b over a. So take the second term, the one that's negative, square root it, and put it over the square root of the very first number, and we're going to have plus or minus our, we're going to get our slope for the two asymptotes, plus or minus, right? Okay, so this is what we know so far, and that's pretty easy, pretty general. But we don't know where the focus points are. We don't know how those focus points determine the curve. Okay, so since the hyperbola oh, I'm sorry, baby girl. You okay? You okay? You gonna be all right? Look, it's you. You're all right. Since the ooh, you stink. Oh my. Since the hyperbola has so much kinship with the ellipse, I think we can make a pretty good guess as to what these two kind of the equivalent parts will be. So if for the ellipse, the focal distance squared is equal to b squared minus a squared, perhaps the focal distance for the hyperbola is going to be b squared plus a squared. Which looks remarkably like a certain equation we may remember from geometry. A squared plus b squared is equal to c squared for the hyperbola. All right, so that might be the case. Again, this is all conjecture right now. The way that we're going to see if it is true is if we can find the focus points and they have some property that helps define the curve. So for the ellipse, any point on the ellipse, draw the two lines to the two focus points, and you get some constant distance. Okay, so perhaps if these focus points exist, we have our hyperbola. Actually, I'm just going to make that straight. Okay. We pick some point on the hyperbola, and I'm just going to assume that the focus points are generally like here-ish and here-ish. Call that F1, F2. Then this would be D1, and this would be D2. Okay. So for the ellipse, D1 plus D2 equaled some constant distance. Our conjecture is going to be that D1 minus D2 equals some constant distance. Let's call it K for now. All right. So far these are conjectures, but let's see if this works. Let's assume that both of these are true and see what happens. So if c squared is going to be equal to b squared plus a squared, all right, well, let's look at our example that we've been dealing with. In this case, a squared is 9, b squared is 4. So 9 plus 4, 9 plus 4, c squared is equal to 9 plus 4. So c squared is equal to 13. So c is equal to plus or minus the square root of 13. All right, I do not like this marker anymore. Okay. So I'm going to get something trustworthy, like a calculator. I'm going to put in 13, square root, and we get 3.6055, etc. All right, so 3.6, 3.61. It's a little bit more than 3.5, which seems to fit what we might expect because it's going to be inside of this curve at the negative, and then inside this curve on the positive. So 3.6, so 3, all right, so that's 3.5, so I'm going to do, so this is potentially F1, and this is potentially F2. All right. And again, those focus points, F1 is negative square root of 13, 0, and F2 is square root of 13, 0. Okay. So now what we're going to do, let's get a different color. We're going to pick some point on our hyperbola that we know, draw straight lines from it to the two focus points, find those distances, subtract them, and see if we get some constant. So we're going to have to actually do this twice in order to prove that it gets some constant. But let's pick the numbers that we kind of already know and already are familiar with. Ooh. Okay, honey? Give me a second. So our conjecture is that the focal distance, c, is going to be, or rather c squared, is going to be equal to the sum of a squared plus b squared. So if that's the case, we got, a squared plus b squared is going to be 9 plus 4, c squared equals 13. So our focal distance should be the square root of 13. We plotted our two focus points. Now, rather than doing the square root of 13, I just approximated it to two decimal places with 3.61 plus or minus for the two focus points. So now the question is, will the focal property also be kind of the inverse of that of the ellipse? The ellipse is that the sum of the two distances from the two focus points to any point on the ellipse, yes, for the ellipse, the sum of the distances is going to be constant. We're going to guess that the difference of the two distances is going to be constant. So if I pick any point on the hyperbola, I picked 2. Let's start here with P1. Now this is one of the points that we found before. This is going to be y equals 1 and x equals, it was like 3 root 5, something like that. Go back to the other video to figure out what it is. But it's approximately 3.35, right? So that's going to be our coordinates for P1. And we're going to see if the difference of these two green lines is some constant. So we have the line from F1 to P1, which I put up here, and then the distance from F2 to P1, which I have written here. And then we're also going to pick another point on the hyperbola. Let's call it point 2, or P2. And we're going to look at the differences of those two distances as well. So F1 to P2, which is down here, and then F2 to P2, which is down here. So I wrote out all the algebra already. There's a lot of writing, so I'm just going to kind of go through it quickly. You can pause the video and verify any of my numbers. Again, I chose not to keep the radicals in an effort to simplify things. So these values are approximate, but so long as we keep the approximations relatively the same, like about two significant figures, and we kind of keep it consistent, we should still get an accurate result, considering what we're trying to do. So if we do the distance formula to find this first green line from F1 to P1, right, as indicated up here, we're going to take the square root and then the difference of the two x's plus, the difference of the two x's quantity squared plus the difference of the two y's quantity squared. All right, so again, there are a lot of decimals, but I thought this would be easier than doing the radicals. But I don't know, maybe a lot of those radicals would have canceled out with all the squaring going on. Anyways, but we end up getting all of this quantity squared is going to be 48.44 plus 1, right? Because 1 squared is 1. We're going to get 49.44, which is approximately equal to 7.03 when we square root it. And then down for the second line, from F2 to P1, we're going to have the same x value for F2 minus the x value for P1, and then plus the difference of the y values quantity squared. This all equals 0.0676 approximately plus 1. We get 1.0676, which when square rooted, we get approximately 1.3. When we take the difference of these two lines, we get this down here. So the first distance minus the second distance, that's approximately 7.03 minus 1.03. We get 6, fortunately, because that's a nice, neat number. Excuse me. All right, now let's see if we pick another point on the hyperbola and then find the difference of those two distances from F1 to P2 and F2 to P2, if we're still going to get 6. So if we look at this first one, I'm not going to walk through all the pieces. You can kind of see it right here. Pause the video if you want to check it out. Anyways, we find the distance from F1 to P2 to be equal to 8.1, again approximately. And then from F2 to P2, we get a distance of 2.1. We find their difference, 8.1 minus 2.1, we get 6 again. That is pretty neat. We made a pretty clever guess that because of the kinship of the hyperbola and the ellipse, that they're going to have their focal properties are going to be related, but not the same. So just as for the ellipse, you take the sum. For the hyperbola, you take the difference. For the general equation in the ellipse, you take a sum, but for the general equation for the hyperbola, you take a difference. And we can kind of see that this is going to consistently be true if we pick more points on the hyperbola and then find the distances to the two foci, take the difference of those distances, we will get some constant. Now, why 6? In this case, it happened to be 6. It didn't have to be. But in this case, it will always be 6. And we can kind of see that there's a corollary here back to the ellipse. If you recall, the sum of those two distances wasn't any random distance. It was the exact distance of the major axis, or 2b, right? If we look at our original equation, because this is horizontal, we should look at the number under the x squared, which is 9. The square root of 9 is 3, which is what determined the distance to these two vertices, right? So this is 3, and this is 3. Well, 2 times 3, or 2a in this case, is 6. So this property holds if we were to pick the distance from here. Say we make this our P3, right? All right, so the distance from P3 to F2 is just going to be that line, and the distance from P3 to the other focus point is going to be that purple line. All right, well, what is the difference of those two lines? Well, this is square root of 13, and so is this. And then this whole thing is 6. So F1 to P3 is 6 root 13, and F2 to P3 is just root 13. If we take the difference of those, we're going to get, sorry, that's not 6 plus, or 6 times, it's 6 plus root 13, excuse me. Now if we take the difference of those, we find that we get, again, the distance between these two vertices, which is 6, just like for the ellipse. All right, so I think that's everything so far. The hyperbola is the last, and in some ways the quirkiest of them. We no longer have a directrix. We no longer have a closed curve, but we have two curves, infinite, open, and they have this asymptotic property. That is, they get closer and closer to the two asymptotes. And we have now know what the focal property is, how the curves are defined. So I'd say we have a pretty good handle on all of the conic sections now. The final video for this unit is going to be an exploration of where all of these different conic sections show up in our world. Not all of them, but some of them that I've kind of seen over the years that I think are really amazing and beautiful. And we are now in a position to appreciate this wonderful characteristic of the conic sections popping up all over the world, precisely because we now have a good handle on all of these conic sections. All right, that's sufficient for the evil of this video.